you so much, Dan. And as you can tell, Dan and I worked together for many years. I thank him. I thank Eric for putting all of this together. Congratulations to the fellows. These are very weird times. Eric and Dan, I wish we could have a real beer together. We can't, but I wish we could. Anyway, working with and talking to this group of fellows, I made a point in my office at the Department of Energy. I ran the Energy Policy and Systems Analysis Office. I actually set it up, ran that office, and had a very, very active fellows program in our office. And we did at MIT, where I worked for about 6.5 years with Secretary Moniz as well. I'm going to cover a broad range of topics. You can see what I was asked to address. And we've already talked a lot about these. Science and data are sending alarms. Urgent action is needed. Last year, it was 108 degrees in Paris. Wow. Okay, 9 of 10 warmest years on record. You can see there. Arctic is warming 2 to 3 times faster than the global average. Sea levels are rising. I like the little greetings from New York postcard there. They've risen 7 to 8 inches since 1900. That could reach 1 to 4 feet by 2100. In May 2019, atmospheric CO2 concentrations reached their highest level in at least 800,000 years. Secretary Chu talked about that. At the current rate of warming, we're going to hit the lower target they talked about in Paris of 1.5 degrees centigrade by 2030. According to the IPCC, impacts on diversity and ecosystems are projected to be lower at 1.5 degrees of global warming compared to 2 degrees. An increase of 2 degrees in global average temperatures means that 37% of the world's population will experience 37% extreme heat compared to 14% at 1.5 degrees. As of 2018, 2/3 of the major emitting countries were not on track to meet their targets. In 2018, US emissions from fossil fuel combustion rose 2.7%. They've gone down again in 2019. I just wanted to give you a little perspective here about what a gigaton means. Okay, 1 gigaton is approximately equal to, in volume, 9 billion barrels of supercritical CO2. That's twice as much as our oil production in the US. Its weight is 12 times the amount of steel manufactured in the US in 2017. And its emissions are the equivalent of 250 million vehicles in 1 year. This is energy-related CO2 emissions from 1990 to 2019. But you can see the advanced economies are in orange, the rest of the world is in gold. And looking at the advanced economies, they've gone way up. The rest of the world has gone way up. The advanced economies have gone down a very small amount. The rest of the world was approximately 10 gigatons of CO2 in 1990, and it's 23 gigatons of CO2 in 2019. So that's a huge difference, okay? And according to the UN, its environmental program, the emissions gap is large. In 2030, annual emissions need to be 15 gigatons lower than current unconditional NDCs imply for the 2 degrees goal, and 32 gigatons lower for 1.5 degrees centigrade goal. And that says 32 gigatons lower. It's 33 gigatons total in 2019. So that gives you some context about the extent of the challenge we're talking about here. This is another slide that shows you the extent of the challenge. This is population growth in the world's 20 most populous countries. I updated this a night before last, okay? The blue boxes here are the numbers for 2019. The numbers next to them are forecasts for population by 2050. What you see here, look at Nigeria. Nigeria becomes the third most populous country on the planet in 2019, in 2050, and replaces the United States, displaces the United States as the third most populous country on the planet. You see that kind of growth in all of Africa, doubling of populations. Nigeria's landmass is 1/6 that of the United States. India, actually I'm going to show you here, these are countries that lose population between now and 2050. China actually loses a little population. India becomes the most populous country on the planet. And to give you a little perspective on that, Modi announced a few years ago, announced a universal access to electricity as a policy in India. That means adding, by 2022, he said universal access to electricity. That means adding 450,000 people or 450 million people in India to the electric grid by 2022, and it gains 500 million people by 2050. So in effect, it means adding almost 1 billion people to an electric grid in the world. Overall, these countries will see a 23% increase in population by 2030. This is US and global urbanization trends, okay? And over on the left, you see US population 1950 to 2050. And the dark green is urban, the light green is rural. And what you see there is rural is flat or declining, and urban population in the United States is going to go up dramatically, already has, okay, up 500% since 1910 alone. This is what's happening around the world. And I would say one thing that was kind of startling to me when I was looking at this, in 2007, for the first time in human history, more human beings live in urban areas. First time in human history, more human beings live in urban areas than in rural areas. And these are increases in urban populations by size and class of settlement. The world's going to add 10 cities of 10 million people or more by 2030. Just so you understand, 4 of those will be in Africa. I'll say a little bit more about Africa in a minute. 326 million cities to 558 and 1 to 5 million. So 220 cities of 1 to 5 million, and about 180 cities of 500 to 1 million. All of this occurs by 2030. So cities need to be a big area of focus, as does providing services in rural areas. Now, this is world primary energy demand by fuel, 2018 and 2040. This is the IEA's current policy scenario, does not include 2-degree targets from Paris and sustainable development scenarios. And this is what's happening in the current policy scenario to fuel sources. Okay, you see there by 2040, coal up 17%, oil up 25%, gas up 48%, nuclear 32%, renewables 97%, solid biomass down. That's good, because that's actually deforestation. Okay, here is a sustainable development scenario. They just put this out. Coal down 61%, oil down 32%, natural gas down just a little bit, 3%. This is by 2040 too. Nuclear up 62%, but it is still dwarfed in comparison to some of the other fuels that you see on energy demand here. Renewables up 215%, and again, solid biomass down 85%. I want to give you some context and perspective about what's going on in the world relative to coal power, coal generation. And this is from 2018. These are coal plants under construction, not announced projects, but coal plants under construction in 2 countries, China and India. They had almost 165,000 megawatts of coal generation under construction in 28. And to put this in perspective, in 2018, the US, its entire coal fleet was 235,000 megawatts of installed capacity. So in 2 countries in 1 year, they have coal plants under construction that are the equivalent of about 2/3 of the entire US coal fleet. I'm going to switch gears a little bit here and talk to you about what we call sustainable energy technologies. And this is for battery storage, lithium-ion battery storage, and metals and minerals that are critical to a renewable energy future. This is from the USGS, US Geological Survey, but the World Bank did a study of wind, solar, and batteries. They put out a study in 2017. They have just released another study, an update of that study that provides more detail. But it was wind, solar, and batteries only. And they looked at the metals and minerals that were required for wind, solar, and batteries. And there were 21 categories of metals and minerals. Rare earths is one of 21 categories. Everyone thinks this is about rare earths. That's not what it's about. It's about a range of metals and minerals. And so they put out a study. China was the #1 resource holder in 11 of those 21 categories, and Australia was #1 resource holder of 5. So that's a little context for what I'm showing you here. This is USGS and lithium production and reserves. And look at the reserves there. United States, these are all in metric tons. United States has 35,000 metric tons. Chile has 8 million metric tons of lithium. And next you have Australia there with 2.7 million tons. Cobalt, we hear a lot about cobalt. US has 38,000 metric tons. Congo has 3.4 million metric tons. And Australia has 1.2 million metric tons of cobalt. Elon Musk didn't like what he was seeing in Congo, and I'll say a little bit more about that in a minute, because children, 5-year-olds, are mining cobalt in Congo. And so he said you can vary the levels, amounts of cobalt and nickel in a lithium-ion battery. He was going to use more nickel and less cobalt. Here are the nickel numbers. We have 110,000 metric tons of nickel in the US. Indonesia has 21 million metric tons of nickel. And here, Brazil has 11 million metric tons of nickel. So just a couple of factoids. Meeting the Clean Energy Ministerial's target of 30 million electric vehicle sales by 2030 would require almost 3 times the 2017 level of cobalt. At those rates, reserves would last for 23 years. So that's just showing you some pull on demand for cobalt. And this is what's happened to lithium prices. When there's a lot of demand, prices go up. There was the price in 2002 was about $2,000 per metric ton. In 2018, it was $18,000 per metric ton. And let me say one other thing about this. And there's been a lot of comparison recently of metals and minerals to peak oil. Okay, this huge demand on metals and minerals for clean energy technologies. And I think that that's an erroneous comparison. And this is the reason why. Peak oil is about fuel. Metals and minerals are about capital costs. you're not using these metals and minerals for fuel. All of these metals and minerals are capital costs for generation or battery technologies. And so what that does say to me is to understand the pull on demand, understanding the lifespan of these technologies rises very high in importance. And I go to the Aspen Energy Institute every summer. One of the CEOs of a large municipal utility was there, and we discussed this issue. And she said, when I buy batteries, utility scale batteries, the manufacturer says the warranty is for 10 years. If I get 3 years out of them, I'm lucky. So among other things, we need to understand more clearly and accurately the lifespan of these technologies in order to understand the pull on demand. These are global greenhouse emissions by economic sector. And you can see there, the highest is electricity and heat production. Next highest, agriculture. And then you've got transportation, industry, and buildings. And this is a little bit more about that. And what happened in 2018, European emissions went down, United States emissions went down, Japan's emissions went down, rest of world's went way up. And after 2 years of growth and unchanged in the economy, the world economy expanded 2.9% in 2019. But we saw a flattening of emissions. That was primarily due to declining emissions from power generation in advanced economies. You can see some of that here, thanks to expanding role of renewable sources, mainly wind and solar, fuel switching from coal to natural gas, and higher nuclear power generation. And also this little table here in the middle, okay, that shows you from when the Kyoto Protocol was committed to in 1997, what the global share of emissions are in 2018, China 28%, US 15.2%. The others are very small relative to those two. Change since the Kyoto Protocol, China up 55%, US down 12%. 69% of that is from coal to gas fuel switching, and the other 31% is from renewable generation. India up 106%, Germany down 12%, and Saudi Arabia, I'm using that as proxy for a large oil producing nation in the Middle East, up 60%. This is US numbers, CO2 emissions in 2017. And greenhouse gas emissions relative to 1990, 91. And what you see there is a peak in 2007 and a huge drop off down in 2009. That just shows you what happens to CO2 emissions when you have a deep recession. That was the deep recession, the Great Recession in the United States. And then here, 2013 to 2017, a small peak in 2013, and then a very steep decline in CO2 emissions there. And with all respect to Secretary Chu, I would say that was the Moniz administration, which I worked in, okay? But he took advantage of a lot of things that Secretary Chu did. Okay, this is the relative contribution by fuel type. And what you can see there, petroleum is 45%. Gas is now 29%. Displaced coal is number 2, and coal then is at 26%. And this is emissions by sector. And our largest emissions are from transportation, 37%. Then electricity at 35%, industry at 17%, and then residential and commercial buildings at 11%. I think this shows you why we really need to focus a whole lot on transportation, electrification of transportation, and our electricity sector. Those are where you're going to get the biggest bang for your buck right now. Secretary Chu mentioned methane emissions. These are methane emissions in 2017. 24% of methane emissions are from gas systems, 6% from petroleum systems. 62% are agriculture and services. We tend to focus only on gas systems on methane emissions, but the real bang for your buck in methane emissions reduction is in agriculture and services, landfill, et cetera, et cetera. We are not developing many technologies to address those issues. Somebody mentioned we did a California study, Eric or somebody, I can't remember. What you see, this is data from the California study, and it's data, not forecast, nothing like that. Red is solar, blue is wind. This is generation for every day of the year in 2017. And the numbers you see popping up are the number of days, excuse me, with little to no wind. And it totals 90 days, as you can see down here. You have 10, 11 days in a row with no wind. And so it's seasonal. We wondered if this was an aberration. We did the same thing for Texas, the wind capital of the United States. It too had 90 days with no wind. It was just at different times of the year. And the reason I raise this, it underscores a challenge with integrating intermittent renewables. What you have here, these are EIA numbers, and on the x-axis is megawatts of power capacity from battery storage, utility scale battery storage. Y-axis is the duration in number of hours. These are regions of the country. PJM, it has 1 hour storage and about 275 megawatts of storage. CAISO, California, has a little bit of 12-hour wind. That's just storage. That's just 3 times linear, 3 times 4-hour storage. Lithium-ion batteries, max 4-hour storage. It's got a bulk of 4-hour storage, and that's about 100 megawatts. Rest of US, you can see that's MISO, where in Chicago and kind of the center of the United States. And it's got about, looks like about 35 megawatts of 1-hour storage. The conclusion from our California study with those kinds of numbers is that you need a fuel at this point in time to reliably operate your electric grid. And right now, that fuel is natural gas. What I would say is it could be hydrogen in the future, a green fuel, although right now we're making hydrogen with natural gas. But it just shows you the inadequacy of current battery storage and the ongoing need for fuel for a reliable grid. This slide is a reference frame. It's not reality, it's a reference frame. We are doing work in New England and looking at renewable portfolio requirements, standards, et cetera, in the states in New England. And it's not to show the probable, it's just to provide you some reference points and context for decision making. And up at the top, that's 2019 installed capacity factors in New England and the average installed capacity and the average capacity factors. Okay, it's 67% gas, 93% capacity factors for gas are 67%, nuclear 93%, oil 15%. And what the reference frame here shows you is if all of your installed capacity for gas, nuclear, and oil were replaced with solar PV at that capacity, those are EIA numbers, how many megawatts of capacity would you need? Okay, and you're looking at about 25,000 megawatts of natural gas, nuclear, and oil. You would need almost 60,000 megawatts of solar PV capacity installed, and you would need 57 square miles of land. Okay, and I looked at square miles because New England is space constrained. Okay, other places are not, New England is, so I looked at square mileage. I did the same thing for onshore wind. This is onshore wind. Has a 35% capacity factor generously. You would need to install 42,000 megawatts of capacity to replace gas, nuclear, and oil, and 194 square miles of land in a space-constrained area. Then I looked at offshore wind. They're very big on offshore wind in that part of the world. Capacity factors there are 45%. And obviously square miles is not an issue, but the number of turbines is an issue. You would need 37,000, almost 38,000, 33,000 megawatts of offshore wind capacity, and you would need 2,183 turbines offshore New England. And I am skeptical that that would happen quickly. We also looked, we looked in the California study at carbon capture and sequestration. This is US nationwide potential carbon sequestration sites. And I've circled generically the MISO region there on the map. And it has very, very good saline formation, potential carbon storage, and it has a lot of depleted oil and gas reservoirs as well. And you can see there the estimated geologic sequestration potential in the United States. Huge amounts of saline formations, far less for oil and natural gas reservoirs and unminable coal seams. We think CCUS is an important technology. Very quickly going through this, these are subnational players committed to the Paris Accord in the United States, and also a slide on net zero policies. What you see on this map, 22 statewide commitments after Trump announced that they were going to get out of the Paris Agreement, which does not take effect until the day after Election Day in 2020. 22 states said we're going to meet Paris targets anyway. The lighter green are states that did not make the commitment, but the largest cities in their states did, and that's 11. Okay, so Atlanta, Georgia made a commitment. So the largest city in Georgia made a commitment to meeting Paris targets. The light blue is city and county commitments, and then the gray is no commitments. For those of you who are still in college, excuse me, 246 institutions of higher learning also made that commitment. These are subnational players that are moving to net zero. What you can see there are 3 states, that's in the statewide green, Hawaii, California, and New York have made commitments to economy-wide carbon neutrality. The electricity neutrality is the dark green outline. New Mexico, where I am today, and it's making me cough, Nevada, Seattle, etc. I think there are 6 states that have committed to electricity, statewide electricity carbon neutrality. And then the filled in blue circle are cities that have made economy-wide carbon neutrality, and the circle outline is electricity carbon neutrality. Just to show you, it's hugely encouraging that many states, cities, counties, et cetera, are making commitments to Paris and to net zero emissions. It also demonstrates for you that it is much more complicated for electricity grid planners, transmission planners, and electricity market operators to operate markets when there are different requirements across the country. After the Green New Deal was put out last year, Secretary Moniz and Andy Karsner, who was an assistant secretary at DOE in the Bush administration, thought that an actionable framework was needed for a Green New Deal. The Green New Deal is a resolution. A resolution is inherently aspirational. We like the aspirations for the Green New Deal for deep decarbonization and for social justice, but it had no actionable infrastructure underneath it. And so they put out an op-ed And I'm going to read you a couple of things from the op-ed. This might go to the point Dan made about practicality, and believe it or not, I actually wrote this sentence. The need for urgency and the disparate impacts of inaction underscores the dangers of magical thinking at either extreme. Climate deniers, as well as those with demonstrably impractical, short-term, feel-good solutions, are moving us sideways when forward motion is essential. And so this is a description. The mission of the Green Real Deal is to provide a framework for accelerating deep decarbonization of energy systems by mid-century in ways that minimize costs, maximize economic opportunities, and promote social equity. It has a set of principles. I've called them out because you can't read them around the center of that circle. The principles are a commitment to technology, policy, and business model innovation, building effective coalitions, addressing all emitting sectors. We tend to focus on electricity because it's the easiest, even though it's hard, ensuring equitable solutions, and promoting optionality and flexibility. One size does not fit all. I'll show you a little bit more about that. Here are the elements of a Green Real Deal, where we are now focusing a lot of our analytical capability at the Energy Futures Initiative, ensuring an equitable transition to a clean energy future, large-scale carbon management systems, assess and support regional and sub-national business and clean energy solutions, support a workforce for a clean energy future, implement fair and effective carbon pricing. I've seen something about how we move forward quickly. Carbon pricing would be a good start. Invest in climate resilient and innovative energy infrastructure. Develop energy innovation portfolios for near-term and breakthrough technologies. And then finally, support sustainable and secure energy supply chains. That's a little bit, and that's our Green Real Deal. What you're seeing here, and I put circles around regions that are in part covered by MISO. These are EIA regions. I could not find out what the rationale was for the regions that they described. And the brown number you see there next to the mountain region, 9.5, that's the average cost of electricity, okay, in cents per price of electricity, in cents per kilowatt hour. The next is percentage of the two largest generation sources in that region. And then you have renewables, non-hydro renewables, and within that you see wind and solar as percentages. So this is a region MISO covers. Two largest generation sources are coal and nuclear, 71%. I would say this is why you need regional solutions. It's 5.5% non-hydro renewables, about 4.6% are wind and solar. So 71% wind and solar, 4.6%, and climate change, addressing climate change and emissions mitigation is urgent. Here you see West South Central, that's natural gas and nuclear, 72%, wind and solar or more. It's about 15% wind and solar, and but still small relative to 72%. West North Central, that is a schizophrenic region. It's the only, it's coal and wind are the two largest generation sources. It is the only region where either wind or solar even come close to being in the top 2%. And you can see there non-hydro renewables is 22%. And the Green Real Deal elements that we are focused on and looking at regional solutions, are assessing and supporting regional subnational solutions, because looking at these numbers, the transition to wind and to clean energy and low emissions, the costs and the technologies will vary greatly between these different regions. 5 regions, nuclear is number 2. That's very helpful when you're talking about zero emissions technologies. Only 1 region, top 2, wind, okay? So transition where you've got a lot of coal, you're probably going to want CCUS there. And that's right, and the other element it addresses is designing and deploying large-scale carbon management. Eric asked that I put a little more information on MISO in here. This is MISO generation capacity in 2018 on the left, the far left box. Next to that is actual generation. If you look at gas in capacity and generation, it's 42% of its capacity, 27% of its generation. That suggests to me that it's using, MISO is using a lot of gas peakers, less natural gas combined cycles for base load. Nuclear is 8% of the capacity, 16% of the generation. That means they're operating full out. Coal also is operating full out, increasing emissions. Wind, not so much. It's only generating about half of its percentage of capacity. That's its capacity factor issue there. And the other thing, MISO, and this is from a study, looked at renewable integration impacts as it increases, and they see a serious inflection point on management operating the grid, energy adequacy and resource adequacy at about 30% penetration of renewable generation. I'm going to switch here to some policies. Right now, there is an expanded, in the US, an expanded 45Q tax credit for carbon capture, utilization, and storage. And what you see here, Congress won't put a tax or a cost on carbon, but it has in 2018, a Republican Congress signed by a Republican president put a value on carbon. That's what this tax credit is about. And it ranges in value up to $50 kiloton of CO2 per year, okay, and up to $50 for geologic storage, $35 for storage for enhanced oil recovery, and then $35 for other utilization processes. I'll tell you there aren't many. And then over here on the left, you see industries as the most difficult sector to decarbonize right now, although agriculture, agriculture is very tough too. But what you see here is first of a kind costs for CCS applied to different types of plants. So you've got this tax credit over here, first of a kind cost for CCS for fertilizer plants, $23 to $33, biomass to ethanol, 21 to 27, and natural gas processing, 20 to 27. So you can compare those first of a kind costs and the value of the tax credit, and you will see how important it is. The problem is this law passed in 2018. The Trump administration has yet to issue a rule and provide guidance for the use of the tax credit, and it expires in 2024. You have to have shovel-ready project ready by 2024 in order to take advantage of it. So there is some urgency. Green Real Deal element, design and deploy large-scale carbon management. I mentioned agriculture being difficult to decarbonize. This is from our California study. The only large-scale technology that we saw for reducing emissions from the agricultural sector by 2030 is renewable gas. Okay, you can see over here the graphs on the left. It's 4.5 megatons of CO2 emissions reductions you can get by using renewable gas. It's also a twofer. It helps you reduce emissions in the agricultural sector, and it also provides you with very low emissions gas for your power generation and other sectors of the economy. And it's a principle. It addresses all emitting sectors. As you saw in the methane emissions that I showed you, we tend to ignore, we focus on gas systems. We are ignoring methane emissions from agriculture and services, landfills, etc., and water treatment. This helps you address all emitting sectors, and it assesses and supports regional and subnational business clean energy solutions. The Midwest, you can't see it very well there. It has a lot of renewable gas potential, not surprisingly as well. I'm almost done. Here we have crosswalked. I have crosswalked opportunities for using existing carbon infrastructure for decarbonization across the top: oil refineries, gas processing, natural gas generation, oil and gas pipelines, ports and storage, and crosswalked those to some key clean energy technologies: biofuels, hydrogen fuel or feedstock here. And then, because I didn't get it all on one page, clean energy technologies, negative emissions technologies, CCUS, renewable natural gas, and smart systems and platforms. And when you look at that crosswalk, you can see hydrogen co-firing can be used in gas generation, existing gas generation, and in gas pipelines. It's limited by volume, but you can use up to 15% hydrogen in gas pipelines with minor upgrades. Oil and gas CCUS technologies, expertise, and its workforce can be used for CCUS. And CCUS and oil and gas production and transport are very similar. Okay, biofuels can be used in existing fuel infrastructure. I already talked about that. Renewable gas processing is similar to natural gas processing. And smart platforms can create smart generation solutions, e.g. managing natural gas and battery hybrids. And the conclusion of this is decarbonization pathways are as much about infrastructure as they are about technology. The transition to a low carbon future could potentially be improved by seeking opportunities to leverage California's existing, this is from California study, physical and intellectual infrastructure, technological expertise, and its skilled and ready workforce. And the elements this addresses: investing in climate resilient and innovative energy infrastructure, supporting the workforce for a clean energy future, and large-scale carbon management systems. This is an example of a hydrogen hub, and we're looking at hydrogen hubs right now. But it's a cartoon. What you can see there, you're producing hydrogen from steam methane reformers and from electrolysis, where you have no emissions. But electrolysis is up to 5 times more expensive than hydrogen from steam reformers. You're doing sequestration, you're doing hydrogen storage. You can use that for petroleum refinery, trucks, ships, and generation. Okay, one central steam methane reforming unit in those volumes and an electrolysis unit could supply half of the Port of LA's and Long Beach's drayage fleet. That's 5,000 trucks, forklifts, et cetera, the entire port's electricity requirement, 80% of Southern Cal Gas's petroleum refiner demand, refiner petroleum demand, 10% of its residential gas demand as a blend, and CO2 sequestration equivalent to half of an average coal plant's emissions. This addresses 3 elements: large-scale carbon management, investing in climate resilient energy infrastructure, and supporting the workforce for a clean energy future. And I talked a while back about metals and minerals and how their capital costs and the need to look at lifespans of these technologies. This is the conclusion of the World Bank study that it put out in 2017, again, updated this year. And in bold, all literature examining material and metals implications for supplying clean energy technologies agrees strongly that building these technologies will result in considerably more material intensive demand than would traditional fossil fuel mechanisms. Simply put, a green technology future is materially intensive, and if not properly managed, could belie the efforts and policies of supplying countries to meet their objectives of meeting climate and related sustainable development goals. It starts begging definitions of what sustainability really means. And what I did, my analysis, I gave this presentation at MIT, a more detailed one on this. My conclusions, you saw the World Bank's conclusions, these are mine. And you saw, I mentioned to you some of the locations of these metals and minerals. increase our diplomatic and investment focus on the Western Hemisphere and Africa, protect supply chains for minerals and metals needed for wind, solar, and batteries. Those supply chains are global. It raises energy security and security issues in general. Support new domestically environmentally responsible mining activities for key minerals and metals. Okay, and I have maps of inactive mines in the United States. I couldn't tell whether they are inactive because the resource was depleted or because they became uneconomic to mine. I asked the CEO of Rio Tinto. His answer to me is they are Superfund sites. So we need some environmentally responsible management and mining. Nevertheless, we have a whole lot of mines in the US. Support innovation in mining efficiency and in earth abundant materials for wind, solar, and batteries. We need new materials that are widely available. Use renewable energy for electricity needed in mining operation. Promote humane mining conditions around the world. I'm going to show you a picture in a minute. I saw it in somebody else's presentation too. Start metals and minerals recycling programs now. This is the picture I wanted to show you. These are the children who are mining cobalt in Democratic Republic of Congo. That's what I mean about humane mining conditions. Another thing I would say is those metals and minerals for clean energy technologies are being shipped. They are being mined in the least developed countries, often in the least developed countries. They are being shipped in with more emissions to the most developed countries, the advanced economies. The CO2 emissions from this mining operation count against Democratic Republic of Congo, not against the recipient of that product. So that's why border adjustments are very important. We need to look at that seriously. These are the two elements that it addresses: an equitable transition to a clean energy future, as demonstrated by this photo, and supporting sustainable and secure clean energy supply chains. So I've talked a long time. I really appreciate this opportunity to talk to you, very important fellows. You're the future energy leaders. And thanks again to all of you, and to Eric and to Dan for this opportunity. Thank you so much.
Thank you, Melanie. Hey, George, do we have time for questions? We've got questions from Zoom, YouTube, Twitter. I mean, there's a lot. Maybe I could review them and Melanie can choose which one she wants to answer. George, what do you think, George?
The easy ones. Review them and I'll answer the easy ones, okay?
The ones are the best ones. That's right. Unfortunately, no easy ones. That may be an outcome. But I would totally agree, Eric and Melanie. Thank you so much. That was exhaustive and encyclopedic almost. But what a background, and what a fertile ground for critical thinking. And I can see you've already done a great deal of it. Yeah, let's have a few questions. And we're already a little bit over. Shall we take another 10 minutes at most? Let's say tentatively. Let's see how we go.
Sure.
But
and
yeah,
by the way, Melanie, I may be following up lots of notes of questions. So okay, here we go. All right. So where did you go? There you are. All right. So first of all, the slides where people were responding, visceral response, just so you know, the coal capacity under construction got a lot of reaction. It looks like your last slide about mining in the Democratic Republic of Congo got a lot of reaction, not as much time, but boy, that surged. And then also your message, I think you'll appreciate, the fellows appreciate this, that the sustainable development scenarios, it's complicated. I think if you're gonna have one message, that's what they're getting. So I thought you should know that's what they're hearing. The questions, I'm gonna read just a few of them. Paul from Fenton, Michigan, saw your slide about renewable development and the constraints and land and such. And yet he wants to know, are we taking full advantage of the existing renewables? So that's question one.
Of which renewables?
Constraints. What's that?
A full advantage of what kind of renewables?
Of the existing renewables that we already have, the wind turbines that we have, the solar panels we have. So he recognizes and appreciates the constraints about the land that you need. But Are we taking full advantage was the question from Paul from Fenton, Michigan. Can I keep going with the questions? Is that okay? So Sandanan from Pune, India asks, it sounds to me that we have a today and a tomorrow problem. Today it's the developed countries. Tomorrow it's the developing countries. He's asking the balance, challenges, where do you focus? It's a tough question. Thank you, Sandanan. I hope. And then Valerie from Allendale, Michigan. She had a question, and I'm going to piggyback on it. She had a great question about carbon capture in the Midwest. You showed some slides, a slide about the opportunities to develop carbon capture in the Midwest. And she asked, there appears to be enormous economic development opportunities for this region to invest in this new sector for jobs, et cetera. I'm going to piggyback on that and add hydrogen. So in addition to carbon capture, what about hydrogen in the Midwest? And then finally, Reed and Sam, the fellows Reed and Sam, they have recognized, they saw your slide about population growth and carbon dioxide emissions. And the question of policy or technological innovation. There's maybe less trust that policy will last and technological innovation lasts forever. So how do you approach, how do you deal with, how do you address this concern about population growth and CO2 emissions when policy takes so long and technological innovation lasts forever? I'll pause with those four, but Thomas, you should be proud. The responses, George, you should be proud. These are just, it's a lot.
Thank you, and I'll be a lot faster than I just was, okay? Because these are I'll give short answers to the question. Use of existing renewables, and in that regard, and you saw this in California, what you're having to see because of the variability of renewables and how they have to be managed, there is curtailment of renewable generation at many times over the course of a year. And in order to maximize the value of existing renewables, you need to minimize the need for curtailment. And my answer to that, and it is a big, broad one, and I'm sorry, it's a policy answer, but I have run the policy office at DOE twice, so I'm a policy person. In the late 90s, we spent a couple of years on electricity market restructuring. It was a nightmare, okay, and a lot of blood on the floor in the electricity restructuring debates. Ultimately, we did. You saw the RTOs and the ISOs on one of my slides. That's part of that restructuring. But that was in the late 90s. I think we need to look at restructuring our electricity markets again. Just think about the technology differences between the late 90s and 2020. They're enormous, okay? And so I think we need to think about restructuring. And what I would say, and we need to easily be able to easily wheel power around the country. And I think you would still need fuel, okay? You saw the 90 days with no wind. You're still going to need fuel for reliable power generation, but you would probably need a lot less of it if you didn't have these segmented market structures and could more easily wheel power around the country. So that's one answer I would give to that question. And the India question, I'm sorry, Eric, could you read that again? I just wrote today and tomorrow down. Okay.
Sure. I'm gonna get, while I get to that question, we're gonna interrupt. We're gonna go to Carly. Carly's gonna actually ask you a question live. Okay. And then also Barbara, but Thomas, let's start with Carly and then we'll go to Barbara next after that. And then we'll get to Sandanan's question from Pune. Go ahead, Carly.
Hi, Sorry, I didn't realize I was going to be asking a question live. I'm just wondering more about the mining of cobalt, lithium, and nickel. You'd spoken specifically about cobalt. So I was wondering if there were also issues with the mining of lithium and cobalt, whether social and environmental, and also as far as the disposal of waste after we're done using these materials, and what's being done to address that.
Well, suffice it to say that these are not green mining operations, okay? And there is a lot of pollution that is created. We have a very significant environmental responsibility structure and policy here in the United States. That is not the case in other countries. And there have been very, very serious accidents in China, for example, from mining accidents where rivers have been polluted, people have died, and not just China, in a lot of different places. Australia has articulated or is articulating a policy for green and net zero mining emissions operations. I haven't looked at that in detail. I just came across it as I was preparing for this talk. I would like to look at that more, and I can guarantee you, Carly, I will make a slide on it when I digest what is involved. But it's not only the labor of 5-year-olds, but these are not all being done in environmentally sensitive in an environmentally sensitive manner, and I think we have to be aware of that as well. And again, all the CO2 emissions that are associated with mining that cobalt accrue to Congo, not to whoever's using the cobalt as in an end-use product. And so I think we need to be mindful of that as well. Another thing I would say on that is I showed that slide. I'm a fellow at the Atlantic Council, a senior fellow at the Atlantic Council, and gave this presentation. There were people in the audience who said, wait a minute, that 5-year-old is earning money. And money is very important, okay? That kind of income is very important. And so I don't want to be a US-centric person looking at all of that, all of those issues. What I am focused on are emissions and clean energy technologies. And it raises a lot of issues about about the sustainability of clean energy. And I mean, another issue is copper. Copper is largely in New Mexico. They've closed the mines here. I'm in New Mexico, but in South America. But we use huge amounts of copper in electric vehicles and in wind turbines. They get struck by lightning all the time. Copper grounds them. And so that's another, it's not just lithium, cobalt and nickel. Copper is another huge issue. And we have a lot of it in the US. So at any rate, that's a long rambling answer. Another question?
Hey, Thomas, you want to go to Barbara next? Barbara?
Yes. So you were mentioning before about the supply chain problem, and I wanted to know how technologies such as solar PV will overcome the challenge in case of high demand and rapid demand, like a lot of demand of solar PV and you don't have enough materials to sell your technology. What are the perspectives related to that?
Well, I would say that supply chains are not inherently bad. We have enormous supply chains for oil around the world. We are developing a global gas market. US has entered into the LNG export market in a big way. And so there are examples, other examples of supply chains. There have been problems with them. You all may or may not remember, I was at DOE at the time. In 2014, Russia cut off natural gas transiting through Ukraine, and that gas was destined in large part for Europe. So there are supply chain issues that do arise, and we have seen them before. We've seen embargoes, et cetera, et cetera. What we do need to be mindful of with these supply chains is that if we are going to rely on them, we need to protect them. I asked my counterpart at the Department of Defense, director of the policy office at DOD in the Obama administration, since we the US have entered the LNG export market in very large ways. 69% of our exports go to OECD countries. They are our trading partners and allies. I asked her, are we doing anything to protect those supply chains? And she said, we are not. Okay, huge number of cargoes are now passing through the Panama Canal. What are we doing to protect the supply chains? So if we're going to rely on other countries for some of these supplies, we need to protect the supply chains. Okay, in a whole range of ways, economically, militarily, policy-wise, diplomatically, et cetera, et cetera. But I also, one of the points I made about what I would do is I would develop earth-abundant materials, okay, for these technologies, develop technologies that use earth-abundant materials. That's another option. We looked at that a lot when I was at MIT. Unfortunately, we don't have a lot of time. We have to address climate change now, so.
Thomas, do you mind if we go to Nathaniel next?
Great. Melanie, I was wondering about whether it makes sense to even consider investing in carbon capture and underground storage when we don't have a price on the pre-existing carbon emissions, just because the cost to do carbon capture is so much higher per ton versus efficiency measures or other measures which can help us avoid those emissions in the first place.
Oh, you're right. We have not put a price on carbon. We have put a value on carbon. That's the one. So there is value in it, but there's nothing that's driving the country to go in that direction. There are, however, 22 states, okay, and the net zero states, et cetera, that have their own policies that I think would provide policy support, okay, for that. So it's not, I think we need a national policy. We don't have one, except for the value that we have put on carbon. And so I think that it is important. I think that what our California study showed is without carbon capture for electricity and industry, California could not meet its 2030 targets. It couldn't even come close. Okay, carbon capture for electricity was the second largest single technology potential emissions reduction out of 33 different technologies that we looked at. So and it's also the largest for industry. So it's a critical technology. I think we need some kind of national clean energy standard, and we don't have one yet, but I think that that's coming, and that will make a difference. Or a fee and dividend, a tax on carbon, okay? But to one other thing that you said, it's so expensive. The EIA's LCOE for plants going into operation in 2022. Natural gas, advanced natural gas combined cycle with carbon capture was $75. Nuclear is nuclear is $93. So 75, 93, that's with carbon capture and storage, the NGCC number. And wind and solar, Lazard did an analysis. You read these, oh, solar is really inexpensive. It is. It doesn't include the cost of storage. And solar PV with storage is like $120, 120 to 140. So that's part of the magical thinking that I refer to in the Green Real Deal op-ed I read for you. And it's very, I think, harmful to say, oh, we should be doing wind and solar because it's a lot cheaper. It's not with storage, and it has to have storage. So,
Eric, can I follow up with a question?
Yeah.
Melanie, you were talking about carbon capture,
right.
and the need for it in the short term because you can't get to 2050 goals without it.
Right.
But how about the long term? Are you thinking that's a transitional technology and ultimately we should not be producing the carbon dioxide at all? Or shall we continue to collect it and bury it, forever?
I think that that it is a technology need that will have a very long tail. Okay, and that when you look at the numbers that I showed you for India and China, for example, those plants, the 265,000 megawatts of coal generation are going to be in existence for the next 40 years. And so developing retrofittable carbon capture technologies, to me, that looks like a huge market opportunity. Okay, but I would note the UK is the first European country to adopt net zero emissions policy. I read its plan and report that they put out in conjunction with that policy. It says carbon capture and sequestration is not only needed, it is essential. Okay, and that's from a country that just committed to net zero emissions. And so they see the value of it. Norway, they've been doing a carbon capture and sequestration in Norway since 2008. It's very viable there. I think to answer your question, it might very well become obsolete. All technologies tend to become obsolete, okay? I was watching a video of some young kids using a rotary phone the other day, and that was very funny, okay? But all technologies become obsolete. I think this is gonna have a very long tail because of the investment required, the huge capital investments in power generation technologies. People are not gonna let those assets be stranded. And in order to not strand those assets, those worker assets as well, and address climate change, you're going to need this for a long time. So.
Great, thank you.
Melanie, you know what? I'm going to ask all the fellows, tell them that they can thank you by buying you a beer when they're out in DC.
Yeah.
So.
Stella.
Drink
Stella.
George and I and Katie and Thomas will be there with our Stellas
okay,
too.
Great.
So. Thank you, Melanie. I hope you don't mind if we follow up with you. There's more questions. We've got more, but we'll follow up. Is that okay?
Can I? It was raised by one of the questions that was asked that before we went to the live questions, and I just want to say something about Africa. And we did a study for Africa, and for an organization that they invest in infrastructure in Africa. 25 countries at the time, they've now expanded to 27. The rural electrification rates in several of those countries that are members of Africa 50 are 7% and under. One country, it is rural electrification is 1%. Okay, urban electrification is quite low. As I mentioned, the 10 cities of 10 million or more. So let's go to the rural or urban areas in Africa. Those 10 cities, 4 are going to be in Africa. They need power, okay, for those large cities. There is a 1-to-1 correlation between the amount of electricity the citizens of a country consume and where it sits on the Human Development Index. Okay, so they are going to provide generation for those cities. They need rural electrification right now. And I went to Kenya to speak to the economic ministers of these countries. They had an annual meeting. I went there to speak to them about a study we did. I took a trip to Rwanda. So I'm flying to East Africa. I'm going to do something fun after I was done. Not that the speech wasn't fun. All speeches are fun, Eric. Okay, but I went to Rwanda, and it's related to this point. Africans are using charcoal for home cooking, home heating, et cetera. They use charcoal. It is deforesting the continent. So our study says you got to stop using charcoal, use LPGs instead. So I go to Rwanda, I do a little tour of the village near my lodge. The first place they took me is where they make the charcoal. Okay, I had zero appreciation for how insinuated that is into the social fabric of rural Africa. And I'm telling you all of this because one, it suggests to me, we've got to give them a little space. We need to help them with technologies to reduce carbon emissions. Importantly, we need to stop the deforestation. And oh, by the way, charcoal kills you. Okay, it's very damaging to health. We've got to stop that deforestation. And we need to provide low cost technologies for some of the least developed countries to move forward with deep decarbonization. It's a huge focus of mine, and I hope others are sensitive to those issues as well. Very important to me, and I just wanted to mention that because it's very important to me. So.